Good morning, everyone. I want to thank my colleagues at Illinois for this invitation to be here today and to give this talk. I had the opportunity to see Nick yesterday with Don Cyphers, who you'll hear from soon. Nick was in great spirits and still pushing the envelope. I mean, when you get with Nick, you come away with all sorts of new ideas, and then you also are refreshed by the stories you heard 40 years ago with a few more details. So life's always interesting when you have a chance to talk to Nick. I'm an Illinois born and bred person. Historically, my French ancestors came from Montreal in 1853 to Illinois, and my German ancestors came from Germany in 1853 as well. So we've been here a while, farming near Kankakee, Illinois. The township that I'm from has no town. It's only 80 miles south of Chicago, but it's a farming community. German, French, Irish people settled in that area when Illinois was not even a state yet. So I was fortunate. When I came to Illinois, I didn't apply anywhere else. I just came to Illinois. I was fortunate to get in very easily. And where I was also fortunate is having great professors here. Met Tim Trick this morning, and one of my professors many years ago. And when I was a junior, I took Nick's first undergraduate course. And the world sort of exploded when I got into his classroom. Because up until then, I was taking double E courses, and they were sort of interesting, but I wasn't turned on to the level of wanting to spend my whole life doing those things. Laplace transforms are wonderful, and the S-plane's a great place to be, but it wasn't where I wanted to spend my life. But when I got to Nick's course, and I started to see what quantum mechanics, quantum effects, electrons, holes, and compound semiconductors could do, I got really excited. So I took a senior level course. And then I was in the middle of trying to decide what to do for grad school, and I went to Nick and I said, could I work in your lab for the summer to get experience? And I was fortunate that one of Nick's grad students had just graduated, and there was a little money left over in a student stipend pile of money he had. He said, yeah, you can work for me. And of course, what I was unknowingly doing is being checked out, right? Can this guy really do anything in the lab? I was top in my class, but can he do anything in the lab? And as you will learn if you look in this very carefully, Nick's students, a lot of them are farm boys who had to learn how to, what a wrench was for. And I have the story in my family where my father wanted to make a 4-row cultivator. And he couldn't afford a 4-row cultivator. It was too expensive. So he bought two 2-row cultivators that were really cheap because no one wanted them anymore. And we had to drill through this tool steel and mate these two cultivators together to make a 4-row cultivator. So when I got to Nick's lab, getting in the lab and building stuff was normal. It was normal for Nick. We built about 30 handmade furnaces, hand-wound the Canthal windings, and had a bunch of variacs growing indium gallium phosphide. The world's first yellow lasers were made out of Nick's lab using student-built widgets that you would look at today and say, that's just junk. You can't do anything with that. Forget about it. But that's part of Nick's creativity, is he can take a sow's ear and make a silk purse, as we say today. So today I'm going to talk about, to some degree, making a silk purse out of a sow's ear, to use a farm reference. MOCVD, as you just learned, is a technology that derived from a chemist at Rockwell International, actually North American Aviation at the time, in California, Harold Manassevit. Manassevit was a PhD chemist from Illinois, not from this school, from Illinois Institute of Technology. And he was specializing in certain types of chemical reactions between Lewis acids and Lewis bases, which some of you may know about. And at Rockwell, at the time, North American Aviation, it was the prime contractor for the Minuteman I, II, and III missiles. So the ICBMs that we were making to protect the country were coming out of a plant near Los Angeles, actually near Disneyland in Orange County in Anaheim, California. And they had a problem. They had circuits that had to pass through nuclear radiation belts due to prior, obviously, nuclear warheads being exploded. And they had to survive and get to their targets. So they needed radiation-hardened circuits. And silicon, like germanium and a lot of semiconductors, when you radiate it really hard, it becomes conducting, and you can't do anything with it. All of your dopants no longer play a role. So Hal's role was to try to create a technology that would allow them to make silicon circuits on an insulating substrate that was going to stay insulating. So he chose sapphire. He has the patent on silicon on sapphire. For many years, silicon on sapphire was a real technology. A lot of companies were developing it. At that same time, gallium arsenide was a known semiconductor, had been since at least the 50s. And it had a similar problem. You couldn't make insulating gallium arsenide, so you had to dope it with chromium atoms, deep acceptors. And the problem is that would type convert back to conducting material. Some part of a boule was conducting, some part insulating. So again, the substrate was the problem, and Manasevich said, well, we'll just use sapphire or an insulating oxide and grow gallium arsenide on that. Well, that was a stupid idea to anyone that was a double E, or even probably a material scientist, but Hal was a chemist, so there's no stupid idea to a chemist. They're always, they're always thinking about bonds and electron clouds and S and P orbitals and D orbitals, and so it's like having a bunch of tinker toys that you can place here and there. So he developed MOCVD. So we're going to talk about that today. The history of MOCVD, I've already sort of gone through briefly, and early semiconductor technologies. As you know now, every semiconductor device you touch today is actually an epitaxial structure, whether it's silicon, silicon germanium, gallium arsenide, indium phosphide, gallium nitride. Anything that you touch is pretty much epitaxial. We don't use bulk semiconductors for devices any longer. And fortunately for us, again, Hal's vision was, I can put single crystal 3-5 semiconductors on any oxide. He did it on diamond. He did it on spinels. He did it on sapphire. He did it on practically everything under the sun that you could think of that would stay insulating at high temperatures and high fluxes of high energy particles. What that led to, I was fortunate to work with him, and he was such a gentleman that when I joined his organization, well, he was a scientist, I was his colleague, he had a lab with some extra space, and he was a hoarder. So every valve he'd ever touched, he still had. Every widget he'd ever seen in his life as a professional is in a storage cabinet. So he let me rummage through his waste bin, and I built a reactor. So this, again, is where Nick's, can you make something out of what looks like trash and use it to make something that's incredibly useful? And fortunately, I had been through that with 2-row cultivators and Nick's furnaces and the kind of epitaxy we did at Illinois. Bob Burnham and others who did the first quaternaries, they were working with tools that you would say, that's not going to work. It's too crude. It always amazed Bell Labs visitors when they visited Nick's lab. They would come into ERL and they would look at 214 lab and say, you did this work in this place? I mean, come on, the windows are leaking dirt. We got window air conditioners because there's no air conditioning. The floor is still the original wood floor full of 30-year-old, 50-year-old, 100-year-old dirt. So I rummaged through his cabinets and built a reactor, and that's the reactor you saw in Fred's picture, which very much is all used stuff except for the tubing. this developed further, as you know now, into a wide variety of commercial reactor systems. There are literally thousands of these in the world today. I'm going to talk about that a little later on. And they've been broadened in their application from my first work on solar cells. My first device was a solar cell, and the next one was an LED, and the next one was a laser. And now they do virtually everything. So we're talking about telecom, power generation, and lighting. Let me try to set the stage again, as other people have done this morning, about where we were in this wonderful history of compound semiconductors. In the 40s and 50s, elemental semiconductors were actually, quote, discovered. The understanding of semiconductors comes after the invention of quantum mechanics, and actually Fred Seitz's work, who was professor of physics here for many years. And the first Pn Junction was an accident. It was an accident made by a double E. Okay, all of this stuff comes from double E's. It doesn't come from physicists or material scientists. It comes from double E's. Here's a double E who's trying to make improved silicon so he can make a device. So he's growing it himself at what's called the Chicken Ranch in Homedale, New Jersey, Bell Labs facility that was down in the remote part of New Jersey, and accidentally makes a crystal that's got impurities in one part that are p-type donor acceptors and other part donors, n-type donors. And he's probing this with probes, and he sees a rectifier, a rectifying effect. No one has seen that before in a semiconductor. Of course, there's point contact rectifiers, but these are different things. And what really shocked him was the photoresponse. Shine a light on it, and the IV curve changes dramatically. After investigation, they discovered they had a Pn junction, and they patented the solar cell. So at that time, the first Pn junction in silicon is discovered. It's an accident by a double E. And then the germanium bipolar transistor. You all know this story here in Illinois about John and his colleagues at Bell Labs looking at what surface states were in silicon and germanium. And finally, in germanium, they discover they can inject holes. And I want to remind you that Bardeen was not a physicist. He had no physics degree. He was engineering physics. He was not a classical physicist. And that observation by Bardeen and Bratton of the first transistor was where John was the first person to identify minority carrier injection. So anytime you turn your lights on or look at your iPhone, you think about minority carrier injection and John, because that's where all this comes from. It was an unknown process until John's discovery of this. And in the same period, around 1950, the first compound semiconductors are identified. There are two groups that have the credit for this. One is at Siemens in Germany named Welker, and the other is a less known woman in Russia at the Yoffie Institute in St. Petersburg, then Leningrad, who discovered these materials in her PhD dissertation. But this is the Cold War. The paper was never published widely in the West, and so Welker gets the credit, but actually it's someone else in Delimova who got that credit, actually. In this wonderful period of 60 to 61, epitaxial growth is invented. Germanium on germanium, germanium on gallium arsenide, but more importantly, Nick's work of ternary gallium arsenide phosphide on other ternaries, gallium arsenide phosphide ternaries. The first real heterojunctions that are useful, direct band gap heterojunctions, are grown by Nick in his little ampules at GE. Again, it's a double E, it's not a physics guy. And at about the same time, liquid phase epitaxy is developed, and Fred mentioned that earlier, and vapor phase epitaxy. So all this happens within this 2-year period. It's sort of like an explosion of material science, engineering, and physics. And in 62, you know, Nick's first visible LEDs, also the first high-efficiency gallium arsenide LEDs were reported, and the first red LEDs and laser diodes. And in a few years later, in 67 to 70, the first heterostructures appear by LPE. MOCVD is developed, and MBE is developed a few years later. So by 1968, Hal Manasevit's paper appeared in APL in January 1968. A few years later, the first MBE papers appear in 1970. So the tools for epitaxy are now available, and then they're exploited heavily in the next 10 years. As you learned about the quaternary, that's invented here in Illinois, down in WRL in 214A by Nick and his students. The quaternary is what you live on today. Take away your quaternaries and you're pretty much sad. Your cell phones don't light up, your rooms don't light up, your exit lights don't light up, your headlights don't light up, your car doesn't work. So quaternary is a big deal. And the first quaternary is aluminum gallium arsenide phosphide, 1970, Burnham and Holonyak and our team. Don Cyphers was there too at the time. And then indium gallium arsenide phosphide quaternary, 1976, and then Allen gap in 1984. And a few years later, of course, now we have the nitride version of the quaternary. So this technology vector over this period of time leads to what I call the Cambrian explosion of solid-state devices. We have the tools, the epitaxial tools, we have the materials, the quaternaries, the ternaries, binary compounds, and we can exploit all of that to make the world's greatest set of transistors, lasers, solar cells, and a lot of other things. This is Hal Manasevit in an early day. I mentioned a chemist. And I want to point out this reactor he has. Most of that's Pyrex tubing with glass stopcock greased valves. That's the technology that was used for SOS, for silicon on sapphire, and the first MOCVD was done that way as well. And he knows he doesn't have safety glasses on either. Well, those are glasses, but we had lots of interesting times in our laboratory because we were using arsine and phosphine and pyrophoric chemicals and actually no sensors, so your nose was the sensor. But this kind of technology is where, when I came into the lab, was a big room with 6 hoods where he had these kind of tools built. I said there's some empty ones, I built mine in there. I sort of learned a lot from him. And it led to this reactor, which you saw a somewhat version of earlier. It runs at atmospheric pressure, uses a quartz chamber, an RF external coil for heating, single susceptor of 2-inch diameter, roughly. A nice fake wood box I built to switch the valves. And you could switch multiple valves at one time with this switch, so you could sort of set up what happens the next time you turn the switch. And all this was hand-built by me, and all the tubing was bent by me, and the fittings were made by me. It was a long-term project, took me a few months to build. But I built this starting in July 1975, and in April, we had an improved version that I'm not showing you here. Basically, what we were doing was using organometallic sources of gallium, aluminum, and zinc as our dopant, and arsine and phosphine to create quaternaries and ternary alloys and binaries, gallium arsenide compounds as well. And the wonderful part about this is you could handle aluminum in a vapor phase technology. Liquid phase epitaxy was the world's highest performance aluminum gallium arsenide technology, but it was limited in many respects by the fact that it was liquid phase epitaxy. It had thermodynamic limitations. And this was a different technology that used different kinds of chemistry and had a much wider range of useful process technology envelopes, so we could move forward. This is a machine that's currently being sold. It has a request for 5 200 millimeter wafers. And there aren't just 1 or 2 of these in the world, there are hundreds of these in the world, and they're working every day. A lot of them are in China right now. So these are the kind of tools that make what you're using today at a cost you can certainly afford to use it. So in Illuminating the World, I'm talking about communications. You all have these. Solar power. These are concentrator cells in the desert in Arizona. You know about solid-state lighting and power and control systems. The next big application for a lot of our MOCVD devices are going to be in your vehicles because they're going to be smart. They're basically computers on wheels, communicating with each other, and information processing. Fred will talk about the photonic integrated circuit, which is the latest incarnation of using compound semiconductors for information transmission. I want to point out that, as Fred already did, that this is a technology or an application space that continues to expand at a phenomenal rate. This is the use of the internet versus year. And yes, there was a time when there was no internet. Hard to imagine today that Google didn't exist, you know, in 1850, but it didn't. And in fact, the intergalactic network, which was actually the real name of the internet, was founded long ago. It was a concept idea by some double E's working with the DARPA at the time. And as you can see, this is a dramatic increase. The first billion users was in 2005. The second billion was in 2010. The third billion in 2014. The fourth billion next year in 2019. An incredible usage rate. And so things just sort of move along, and you can imagine it's not going to roll over anytime soon. And why is that? Well, here's a story about this. Internet penetration isn't saturated. These are the rates of penetration versus geographic region in 2017. As you can see, North America is pretty well developed, but there's a lot of the world, a lot of people in Asia who are not served well, in Africa, and the world average is still around 52% usage. And this is on the far right, by geographic region, the number of users, as you can see, dominated by Asia, but still only less than 50% access. The internet capacity is supported by literally millions of MOCVD grown devices, and this is a plot of the traffic capacity for the global internet. You can see that it's very well developed between North America and Europe, but a lot less developed for other parts of the world. So still a lot of things to be done. And to put this in more wider perspective, the value to the world is extremely large. This is from 2017, the global digital snapshot of about 54% of the world's population has access to the World Wide Web. About 50% have internet users are 3.7, roughly 3.8 billion users. Social media, which is one of the big application spaces, 38% penetration. Unique mobile users, 66%. A lot of you have more than one cell phone, more than one account. And active mobile social users, only 34% penetration. So you see there's a lot of people still needing to get access. Of course, cell phones aren't really new. And here's an example of some that have been found in the Euphrates Valley where agriculture was first developed many years ago. You see they have a cell phone there. So this is not really brand new technology, but having it so accessible to everybody is brand new. Those are probably kings and queens who had their cell phones. One of the bigger application spaces that we have seen, and this is a technology that uses a lot of interesting things, including Nick's oxide. This is the vertical cavity surface emitting laser, and it has basically been developed over many years, mostly by MOCVD now. In fact, as far as I know, entirely by MOCVD, as far as the biggest application. And you can see a variety of uses for these devices, a variety of wavelengths. And the latest thing that we all see is in an iPhone 10, you'll see a VCSEL array that looks at your face and identifies you and opens your phone automatically. And you can't fool it. You can't fool it. I've never been able to fool it, and no one's I know has been able to fool it. Maybe you could 3D print your face and get it to work. I haven't tried that, but a picture won't work. We're actually, in my group, we're trying to make an ultraviolet VCSEL. And why would you want that? Well, there are such things as atomic clocks, and we need to make an atomic clock with the ytterbium atoms that requires a 369.5 nanometer VCSEL. So far, it's an impossible task, but my students will get their PhDs, hopefully, and we'll have that device soon. To give you more information on what Apple's doing, and now other companies as well, is using these infrared VCSELs to do facial recognition. There's a dot projector there on the far right, which is a VCSEL array, all grown by MOCVD. Obviously, there's a bunch of other stuff there that uses 3.5 compound semiconductors, like the infrared camera, flood illuminators, and all that. MOCVD is virtually ideal for these large area epitaxial structures that I showed you from that large reactor, and you can make large arrays of VCSELs. In fact, strange enough, you can make heaters out of VCSELs. So here's a 1.6 kilowatt industrial heater that uses a full 3-inch wafer full of VCSELs and 100% yield. So amazing technology when you consider what's actually in this device. As you can see, there's a cross-section there here in the upper left corner of the Pn Junction and the layers involved in a VCSEL technology. Another application space that's less known to people, but certainly should be, is the use of MOCVD-grown solar cells. This shows a plot of solar cell efficiency versus year for all the technologies that have been developed. It doesn't show the first solar cell, which is this Pn Junction that was made by Russell All at Bell Labs in 1940. But commercial cells, starting with RCA's silicon cells here around 1976, and then moving on. The biggest, highest performance cells are all MOCVD grown, and as you can see, they're basically compound semiconductor multi-junction cells, and up to 3 and 4 junctions now, which have the world's record efficiency. Very complicated epitaxial structures with multiple tunnel junctions and several different materials technology layers involved. So where does that stuff take us? Well, it takes us to outer space. As I mentioned earlier, also concentrator cells on Earth. Today, virtually every near-Earth satellite, in fact, I think every satellite that's in near-Earth orbit today uses compound semiconductors as their solar cell materials grown by MOCVD. And future cells are going to be even more efficient. What we have also is some rather exotic applications for 3.5 MOCVD grown cells, including the solar car race, an airplane that flies entirely on solar energy, has flown around the world nonstop, solar impulse too. And out on Mars, there's still enough light for a solar cell array to power these little robots that run around, the Mars rovers, Opportunity and Spirit. They use gallium arsenide-based multi-junction cells. And of course, they've explored the planet for many years, much longer than was originally designed for. So at least one of them, Spirit, died a while ago. They lost communication with it. Opportunity was asleep for a while because of a Mars dust storm that covered the solar panel. And then a dust storm came. I guess the wind blew the dust off, and now it's back alive, I understand. But not everybody's happy with this. The Martians are upset that we've got these devices rolling around on their planet, and we didn't ask for permission. But nevertheless, I think they've given us a lot of information on what's going on Mars. The future, again, is extremely interesting because there are several companies offering, or will be offering, high-speed World Wide Web access, literally worldwide, any point on the globe using satellite technology. Instead of the fibers that we plow into the ocean floor, everything will go up in space. And all of these systems on a commercially developed satellite for telecom basically rely on 3.5 compound semiconductors, including the RF part of this device. And this is one example. OneWeb is a company that's developing a 900 satellite constellation where they'll have total global coverage. So if you're in Iceland somewhere, or Greenland, or Antarctica, or the Fiji Islands, it'll look like you're in downtown Chicago with web access anywhere you want it, high-speed digital access. So this is not just one company. There's several companies building 900-plus satellite arrays that are going to be up in space, probably launched by SpaceX, Elon Musk's company. You're all familiar with this spectrum in the visible and near infrared and near IR region. And this label shows all important recent devices where MOCVD plays a role in either light emission or light detection or both. And we're pushing that, of course, farther and farther in the infrared to 13 microns with quantum cascade lasers going by MOCVD. So even this is expanding. Right now, we're trying to push down to 250 and below for detecting photons from the systems being built for neutrino detection using liquid argon, tons of liquid argon as a detector for neutrinos. This shows the LED market. You've seen Fred's talk about this. Is the LED market by package application versus year. And as Fred showed, it's sort of tapering off. But what's not shown here, as he said, is that soon there will be, your cell phone display will be all LED. It won't just be LED backlighting a LCD panel or organic OLED display. It'll be a full inorganic LED micro display. And cars' headlights won't be single chips or 6 chips. There'll be thousands of LEDs in a car headlight. So it'll be interesting to see how this plays out in the future. Of course, what has happened is that we used to have in our offices like a table lamp, maybe a ceiling lamp, and that was about it. And then the outside of the building was dark. But now everybody wants to light up the outside of the building. So if you go to China, for example, you'll see the latest constructions. They're virtually all architectural marvels with some sort of external illumination at night to present that fantastic architecture to people in 24/7. So I think there's a lot of things left to be done to even expand what lighting solutions we have for normal applications like buildings. There's still a lot of places we can go. I mentioned this earlier with a picture, the same picture actually, about where we're going to go with autonomous vehicles. And pretty much those systems are going to use a lot of compound semiconductor sensors. They'll probably use LiDAR systems that are MOCVD-grown detectors and emitters. They'll be using very efficient power generation and control systems, stabilizers of various kinds. So I think this whole thing is going to just keep expanding as we find more uses. This is a slide that refers to the sort of end of Moore's law problem we have, and it shows you graphically what the number of chips and performance of chips has done versus time. And it's actually rolled over, as you can see. Even though we're shrinking the device now to, this shows 16 nanometers. Of course, the next node is 5 nanometer node. and then 3 nanometer node, and then there's by the way, there's something that we all refer to as the red brick wall that was referred to earlier, where you don't know what you're going to do 2 years from now for Moore's law. It's sort of like the red brick wall keeps moving because people get really innovative how they do things. And so size matters, but at some point we're down to a gate length that's 4 atoms wide. How do you handle that? That's basically a quantum computer in some form, right? It's a different kind of quantum computer than what people refer to, but it's quantum mechanics controlling your device structure. And I have some information, I think from reliable sources, that the next step beyond this into 5 and 3 nanometer node is going to use indium arsenide MOCVD grown channels on silicon ICs. So MOCVD will become everybody's answer. Even the silicon people have to use it to make the next steps. So Moore's law is coming to an end, and the solution has been for many years to just keep on making silicon smaller, maybe do silicon germanium, but that's going to end too because the gate length problem is not solvable in the trivial way it has been. I say trivial, the straightforward way. So the solution is to get higher mobility materials like 3-5 semiconductors, integrate them with silicon CMOS. And that's sort of what people are thinking about. This is an older slide from Intel showing that somewhere around last year, we were supposed to be seeing quantum well 3-5 devices on silicon or some sort of nanowires and maybe graphene. So there's still a lot of unknown things out there. The red brick wall keeps moving along, but it's still hard to see what's over the red brick wall. And so all of these things are being studied. But I've been told by some of my ex-students who are now working for TSMC or Intel that indium arsenide channels are going to be part of the solution, at least for 3 nanometer node. So where does this put MOCVD epitaxy? Well, the epitaxy wafer market has grown to over $4 billion, and as LED lighting itself zooms to beyond $80 billion, this shows the epi wafer market versus wafer size versus year. As you can see, there's sort of a dramatic change over the last few years, going more and more on 6 and 8 inch wafers. I show you the lecture with 5 8-inch wafers in a single run. That's probably going to increase sometime in the near future. And how about the number of MOCVD reactors? Well, this is sort of what was known in 2015. And people, of course, often don't reveal how many reactors they have, but this is the best guess for a variety of companies, beginning with Epistar. T is Taiwan, K is Korea, C is China, J is Japan, G is Germany, H, K is Hong Kong. You can see what has happened is that a lot of this technology has developed here in the US, has moved to Hong Kong, Korea, China. This is again 2015, and again could be inaccurate. There are error bars probably on this, but today Nichia is never. It's all speculation on what Nichia is doing. So I put a Nichia's bar over there with a question mark on it. Nichia is, of course, the historical first supplier of blue LEDs, first supplier of blue laser diodes in the world. I was just in China for a meeting, and I learned that Sanan now has over 400 reactors, and HC Semitech has over 240. So these are the big players in China. As you can see, Epistar in Taiwan had about 450 in 2015, but I think a lot of those were smaller reactors. These new bars I put in are those big 5 by 200 millimeter systems. So my story is MOCVD provides illumination for everyone virtually on the planet now in some form, either information illumination or lighting illumination or communication illumination. And I borrowed this from Sherwin-Williams, modified their paint can. So MOCVD covers the earth. So thank you for your attention. Happy to answer questions if you have them. And I welcome you to Atlanta at Georgia Tech. And we have a campus in Shenzhen and a campus in Lorraine, France, and Metz, so you can visit us all over the planet. Thank you.